Welcome to this week's Maritime Innovation Update. I'm Steffen, your host. And today we are hearing a presentation about automatic speech recognition in the context of maritime radio communication. And this will be presented by my dear colleague Emin. Hi, Emin. And please, as always, this session will be recorded, so you can watch it later online. And please turn off your microphone and camera if you already haven't. And I would say, Emin, let's start. And I will give over to you. And please, if you have any questions about the presentation or about the CML, our research, please write in the chat, and we will have a discussion at the end, or we will contact you. Have fun and enjoy.
Thank you, Steffen. First to introduce myself, my name is Emin Nakilcioğlu. I'm a research associate at Fraunhofer CML, and today I'm going to talk about a project we work on, which is about automatic speech recognition for maritime communication. So today's agenda is to give you a little bit intro to the maritime communications, and then we will move on to data processing that we use for our automatic speech recognition, and then the principles and the architectures we use for our speech recognizer, and at the end I will finish it off with our software that we have right now. So for those who are not familiar with the maritime communication, it is a communication done through a radio called VHF radio, which is very high frequency. It stands for very high frequency. You can also see on the picture that's a VHF radio operator. It is standard communication for ships, and it's mandatory to have on board. It is relatively a robust technology, but I will give you a little bit of how it sounds on the ship.
Small boat Yankee, sector North New England, channel 16 over. Yeah, this is Swamp Yankee. I got a no start and I'm taking on water just off from 2KR. Over.
That's, give or take what you hear on board, depending on the distance between two communicators and other factors. But it is, as you already realized probably, it's heavy background noise is present during communication. Since it is an international industry, you will hear a lot of accents, dialects, even in the same country borders, you will hear different dialects. On top of that, there is a certain phrases that's specific to maritime communication, which is called standard maritime communication phrases. To give you a little example, for example, if you were to the first sentence, if you were to put it in a regular English speech, you would use my present speed is 14 knots, and I correct myself, my present speed is blah blah. But it's a little bit different in communication, maritime communication, for efficiency purposes and some other purposes probably for them. And for example, I put the second sentence here to give you an idea. If you say boy 033, it would be boy as a son or something, it's a male kid. But in maritime context, it will be the boy that's floating on the water. So how do we deal with that data? The main part of the main part we have to deal with of data is this noise part. For that, signal quantity affects the noise, nature of the data as well. And then we will need labels for further purposes for our trainings, but I will get back to that later on. The quality of the data, or the nature of the quality of the data will change depending on your hardware capacity. Again, as I mentioned, the distance between two communicators. So what we have is on the right side, you will see frequency representation of the audio signal. And what we deal with is something called phones. Each phone has its own frequency, let's say map, and we want to map all these analog audio to our speech recognizer, so we can, at the end, have a speech recognizer that can understand these signals as words, first as phones and then as words. To address this noise, we use a library from Python. It is basically a noise gating, and there are two available applications for this noise reduction, one being stationary and one being non-stationary, which means the stationary one is just you take a sample from your audio, and then you create some noise map, per se, and then you apply this noise map to your entire audio, and then you will therefore reduce the noise. This is the stationary one, so-called static. And the secondary one is the non-stationary one, is having a window of, you have a window, you decide how many seconds you want as your window, and then this window will slide to, map out the noise characteristics of your audio as much as it can, and then you will apply this noise gate every time you have new window. You create your map noise characteristics, and then you apply your gate, and then you will have noise reduced audio. On the right side, you will see how you can visualize these noise gates applied on the audio. First one is having like a really heavy audio, and then if you apply a stationary one, a static one, there were some kind of noise reductions in some part, and some part the heavy noise is still present. And with the non-stationary one, you have a relatively better outcome of noise reduction. So this is the main noise reduction application we use. We have personally tried to use noisy data and clean data. We have concluded that the clean data, the model that trained with the clean data performs quite better than a model that's trained by using noisy data. That's why we went on to using clean data. So to give you a little bit about the basics of the speech recognition, historically, speech recognition is the system that produced the ASR, or the speech recognizer, produce the most likely word sequence given an incoming speech signal. You will see the incoming speech signal, and then we first apply front-end processing, which is the vectorization of these analog signals, so that we can digitalize it, and then we can feed onto the machine. In our case, the decoder. And this decoder has historically had three main parts, one being acoustic model that is responsible for the acoustic representation of the input. Second one is the language model that gives the context between words and the language. And the lexicon, you can think of as a dictionary that has all these words that language model can use. So this is the first the traditional approach to automatic speech recognition. And then it has the downside of this application, one of them being you have to always retrain your model if you happen to have like new data. It's also hard to have like multilingual decoder. You would only have decoder that can decode one language. So for that, for the recent years, there's a architecture that's been developed by Facebook. It's called Wave 2 Vec 2. Basic approach behind that architecture is to have a two-phase training. So the first phase of the training is the self-supervised training. As the name suggests, the model teaches itself. Teaches itself. Yeah. Well, you don't have a label, which in our case, a transcription of the audio input you put in. You just have audio input, and for the self-supervised learning, the model try to understand the nature of the input. And then for the second part of the training, you are fine-tuning the trained model using a transcription, audio data with transcriptions. So that kind of addresses one of the problems I forgot to mention with the traditional approach, is that you always need data with labels. Labels in our case, again, the transcriptions of the audio files. Since we can train a speech recognition model without labels as our first phase, it addresses this problem. And you can have hours of data without the label. It's easy to find, but it's tough to find a label data in audio cases. So with the Wave 2 Vec 2 approach, you can train a model only using audio files, and then you fine-tune it with your audio data with transcriptions. In the original paper, they have used around 50 to 60 hours of only audio data to perform the self-supervised training, and then they used around 10 minutes to 1 hour of labeled data, and they were able to perform better than the traditional approaches regarding English language. Exactly. So how did we use in our case? So one of the things with the Wave 2 Vec 2 architecture and what they use, which is called transformers, is that you can do something called transfer learning, which means you can train a model, and then you can take this trained model and fine-tune it, which is the transfer learning part. It kind of gives us, researchers like us, with not really have big capacity of training, an opportunity to get this pre-trained model, because we cannot train that big of a model, and then fine-tuning for our purposes, which is what we do. We gather information, Maritime information, Maritime audio data, and the transcription of that audio data. And now we use that data to fine-tune a pre-trained Wave 2 Vec 2 model. And then at the end, we have our own model, which we call MAR-FM, that can transcribe audio files, Maritime communications, rather than not fine-tuned audio models, speech recognizers. This is a look to our application, one of the better applications. What you see here is the transcription box, let's say. One of the pluses we can do is we can transcribe both German and English language at the same time. It can even translate Denglish to some extent, which means you can start an English sentence, you go on to German sentence, and then you go on to English sentence again. All will be able to transcribe it, because since we've used multilingual data and multilingual training, German and English is kind of a one combined language for the speech recognizer. So it can transcribe both languages simultaneously. If we have time at the end, I will show you a little demonstration again, but first we may take up a couple of questions if you guys may have, and thank you for your attention.
Yeah, thank you, Emin. So yeah, feel free to post questions in the chat. So yeah, Emin, maybe you can elaborate a bit more about the current performance of the model? So, like you said, noise reduction plays a big role. Are there other challenges, like, for example, different accents of English? Because we know there are many nationalities on the radio messages.
Exactly. That's a great question. Thank you again for the question. So since we use this training data for fine tuning, so that the nature of the training data, also the pre-training data, kind of gives the nature of the speech recognizer as well. What kind of accent is included in that data, you can expect model is going to learn. But it will be not realistically expect the model to understand one accent that's not being taught before. It's not going to happen unless the recognizer heard or trained by this accent first. It may recognize it, otherwise it's not going to happen. We tried it, it's not happening in our case at least, for the approach we take. So every time we have a couple of research projects and also some project partners. So we always ask them to have some kind of data from their base, because every base have their own nature of, let's say, visitors. If you're, let's say, a Finnish BTS center, you will have different kind of visitors. If you have a German business center, you have different kind of. So yeah, accent is a big issue we also address if we have the necessary data that we can work with. Otherwise, it will be tough.
Yeah, okay, understand. So there's a question in the chat. So we were using the Wave 2 MEC2 model. Did you also consider more recent publications, for example, Whisper, the Whisper model?
Yeah, actually, in the meantime, we are also, it's like a side project. We also want to see if Whisper, fine-tuning a Whisper can benefit us more. We are also working on having a fine-tuned Whisper model as well, because they have similar architectures. One can fine-tune a Whisper model as well. So, but yeah, we are actually currently working on having a fine-tuned Whisper model too. But we'll see how that's gonna benefit us, or how better or worse gonna perform compared to our way to model.
Yeah. Okay. So another question for you. So, for example, what happens if the language of the sentence is mixed up? So there are, for example, there are German words, and then there pops up an English word or in some other language. How will the model handle that?
I mean, we can actually try and see. 1 second. Help, mein Engine stoppt zu funktionieren.
Yeah, okay.
Help, mein Engine stoppt zu funktionieren.
Okay, apparently it is working. Great.
Exactly. It's nice to see. Of course, it's always tough to have a live demo. But yeah, you can understand both of them family. So it couldn't catch the mine engine, just an engine, but still, there's something to work on.
And are you still growing the database? So the amount of data, will there be continuously new data? So will the model always grow?
Yeah, exactly. So it's, for example, this is our German model. We're also working on a Finnish model, which the Finnish and English multilingual. So it always depends who we are working with. In a project, we're working with a Finnish partners. So we are creating a Finnish-based speech recognizer. And at the moment, well, we're really, satisfied with the performance of a German English model. But if in the future it becomes like not an up-to-date model, it couldn't catch the current speech patterns, and then we may need to update it as well. But again, we will need the current data for that too. But this is a question if in the future, if that's the case, if our model started to perform relatively worse. But it's easy to brief fine-tune our model.
Yeah, right. Yeah, I would say we are out of time, and thank you everybody for your attention. Of course, feel free to contact us via our website, posted in the chat, or you can review all the videos of the Maritime Innovation Update online. And yeah, then have a nice day and a nice weekend.
Thank you. Thank you.
Yeah.
Have a nice weekend.
Thank you again, Emin.
Thank you, Stefan.